In this video, we're going to continue the discussion of how to work with continuous functions in our linear vector spaces formalism. So we already worked on the actual vectors. Now what I want to talk about is the operators. So how do we work with operators in infinite dimensions? Okay, so we already, like I said, we already developed the vectors, and so now we can write down essentially an operator that operates on a vector of infinite dimensions and transforms it into another vector of infinite dimensions, where I'll put a little tilde on top to show that that's the final state, or that's the new vector. So one example of this, which we're going to focus on, is the derivative. What if I want to take a derivative of a continuous function, or a derivative of a vector that has infinite dimensions? And so we can think about this now in the usual form, which is that our function tilde, as a function of x, is the derivative of the function f with respect to x. Okay, that's a transformation. I'm transforming one function into another function. So let's write this down now in our vector formalism and say I have an operator d operating on the vector f, which is essentially creating a state which I'll label as the derivative of f with respect to x. And so what we want to do is find the matrix form of d in some basis x. So we can make the product of x with our transformed vector, which is another way of writing it as this way right here. So I'm taking the product of x with the derivative, which is now going to give us our function that's been where we've taken the derivative of f. Okay. So we can write this out like we did before and say that we can introduce the projection operator, or the identity really. And so we introduce the identity, which can be thrown in into any vector because the identity operator doesn't change that vector. And then we can write it as the sum or integral of the projection into the x prime space, and then we have to integrate over all of the x prime space. So we take this integral. And that should still give us a derivative of the function back again. So now the derivative of this function f is defined as the integral of moving the operator from one space to another, and then projecting the vector f onto some space. In this case, I'll call it x prime. So we have to look at these different pieces. So we can look at the first, we can look at this piece, which is our operator operating on the basis x prime, and then projected onto, or the product of x. Okay, so let's do that. Let's take a look at that piece. And so this I'm going to write as a, let's see, I will write that as the Dirac delta function, the derivative of the Dirac delta function. So we use the prime, x minus x prime. And if you remember from the previous class, the identity is that the derivative of the Dirac delta function is the Dirac delta function back again times the derivative in the other basis. So we move from taking a derivative in the x basis to a derivative in the x prime basis. And we can label that now as our matrix element dx x prime. So if we put all this together, so we substitute that back into the integral, and the integral becomes the Dirac delta function, the derivative in x prime space, operating on the function in x prime space, integrating over x prime space. So that one step you may remember is this function is the product of f in x prime, is the product, is projecting that f into x prime space. Okay, so when we do that, we now have to take the derivative of the function in x prime space, but when we do that, what we get is multiplying by the Dirac delta function and integrating. This becomes the derivative of the function in x prime space where x prime is equal to x, or the derivative of f with respect to x. Okay, so that's what we've achieved. We've achieved starting with writing it down as vectors and then working our way into functions like the Dirac delta function and the derivative of the function f. And now we've been able to define our derivative with respect to x. So one question you can ask is this new operator D, is it Hermitian? Well, if it is Hermitian, then the matrix element x prime should be equal to the complex conjugate of x prime x. So I should be able to get transpose and then, complex conjugate, but it should be equal. But unfortunately, this isn't true. Okay, why isn't this true? Well, it's not true because if I go back to my original starting point, then what we have is the derivative of the Dirac delta function. And then I'll take the complex conjugate of it and transpose those indices. And what I should get then is a transpose of the indices, then the complex conjugate right there. Okay, so if that was true, then we would have essentially the derivative. So there's nothing about the Dirac delta function which is complex. It's a real function. So taking the complex conjugate doesn't change it, but we've switched the indices. And then, if you remember, that this is the derivative with respect to x of our Dirac delta function. Okay. Now, when I take that, I apply the chain rule, and I get minus x prime minus x and I get this minus sign, and it's the derivative. I'll call it's the derivative back again. So it turns out that it's not. D is not Hermitian. When you do the transpose of it, then you would get a negative sign. You get anti-Hermitian, really. And so what can we do to change that? Well, one thing we can do is we can kind of just start throwing stuff in and see what helps. So let's redefine this k as minus sign. That'll help with the minus sign. And we'll make it a minus I, like so. So that's going to help when we take the complex conjugate. It'll change the sign of it, and all the signs should work out. So if you see what I mean, so let's say we have the matrix element k x prime x, and then we take the complex conjugate of it. That would be minus I, the Dirac delta function, derivative x prime minus x, take the complex conjugate of that. So then that would give me a plus I. The complex conjugate turns all i's into minus i's. So I change the minus sign, and I don't do anything to the derivative part. The delta function is real. And so now when I switch back from x prime to x, then what do I get? I get minus I x minus x prime. So that's what I missed earlier, sorry. Up here, that minus sign came about because now I'm switching, going back to the original derivative of the Dirac delta function. So in this case, when I switch back, I get the minus sign back again, and lo and behold, I get k x x prime. And so by taking a minus I times the derivative operator gives me a Hermitian derivative operator. So what we have then is k is a derivative operator, and it is Hermitian. So what we're going to do is take a look at this and see how the k operator works, and see what we can learn about it. So the one thing we can do is consider two vectors. F and G in a range of x going from A to B. So let's take a look. How does our derivative operator work on these two states? So I'm not going to be able to get too much far in this video, but essentially the next step is to operate with K on F and then take the product with G. So operate K on F and then I keep saying project it onto G. And so if K is Hermitian, then what we can do is we can switch these around. So I'm going to put the K inside with the F, and then I'm going to notice that I could switch this around to KFG complex conjugate. But if K is Hermitian, then what we would get is FK adjoint of G, which is now basically the same thing as saying this if K is equal to K base its complex conjugate or its Hermitian. So if K is a Hermitian operator, then we can do this kind of exercise where we basically turn around the product, and K should still act the same way on G as it would on F if it is Hermitian. If it is a function where is an operator that is equal to its own adjoint. So I'm going to stop here, and then I'll pick this up in the next video.